Hi everyone, welcome back. In the last video of the series, we saw um, the range migration algorithm, the theory behind the algorithm basically on how to do fast 3D SAR imaging, show that it's really fast compared to back projection. So in this video, I thought I'll show you the experimental setup that I had that we used to generate some data and then actually apply the algorithm on some experimental results. So you can actually get an idea of what it looks like to use it. I'll also show you the MATLAB implementation and provide codes and the data that you can use for your own interest to explore um, this algorithm. Okay, I just want to mention briefly that the data and algorithm along with the system details and calibration is already published in a paper recently that you can look at, which is shown here. But you don't have to. I'll cover all the bases needed and provide the code in this video as well. Okay, so I'm not going to go through the theory again. You should watch that video. Definitely watch the video before you try the code for yourself and before you even start this video. So I would suggest go finish that and come back and watch this. Okay, so we saw that it's a simple three-step algorithm. We take a 2D FFT, do the stalled interpolation, and then 3D inverse FFT, and we'll implement this in code. I'll also talk about some of the K-space that we use, K-space sampling stuff that we did. Okay, so without further delay, let's get started. So this is what it looks like. I'll provide this on GitHub. I just want to mention that a very similar code already exists on my GitHub, which I used for the paper. It's very similar. It uses the same data set, but I suggest using this code instead because this is a bit cleaner and the exposition is a little better on this code. Okay, so we start by maybe first I'll actually cover the system itself. So this is what the system looks like. For full details, you can look at the paper, but it's pretty simple. You have a common reference that generates a clock, and the clock is used to synchronize two PLLs, singleton PLLs. Microcontroller controls everything, and then the chirp is originally made by a DDS unit. It's filtered and then mixes with this to a higher frequency. We use the down chirp image. So whenever you have a chirp that mixed with a single frequency, you get an up chirp and a down chirp, if you think about it. Here, in fact, because of the filter we had lying around, we used the down chirp. And this is something to keep in mind when we look at the code. Anyway, so the down chirp from 6.3 to 7 gigahertz is used, filtered, amplified, multiplied by a factor of 2, filtered again, divided into TX and RX paths. In the TX path, it's multiplied by 6, filtered, and then transmitted from the antenna. That goes, hits the target or whatever, comes back, gets amplified, and then mixed with the down chirp. So this is the de-chirping part happens here. And then there's actually a filter as well here, which I haven't shown. Filtered out, amplified, and then goes to the sampler. Here's the experimental setup. So the IF system is here, the computer is here, sampler is out here, and then I have the RF front end sitting on an XY stage. And the XY stage, collects data over a raster scan. So I've used the stop and go approximation. I am using a stop and go system. Stops at a location, collects data, moves to the next location, collects over a raster scan of 2D on a 2D surface like this. And that it's important to keep in mind that this is in fact a raster scan data when we go to the code. Okay, so the IF signal comes out, is sampled and directly stored in memory of this computer. So I've done 5 different experiments with 5 different targets. So I have a Siemens stencil as one target sitting on a foam block. Another target is a University of Michigan symbol or a logo M cut out from a piece of metal. I have a 3D printed handgun. This is not an actual handgun. I mean, it's just 3D printed block of plastic really in the shape of a handgun. Sprayed it with some copper to make it reflective. And then the same handgun, the back side of the gun has this copper tape for historical reasons. I'm not actually using it sitting inside a cardboard box. So it's totally concealed. And then at a separate distance, I have this stencil attached to the back of the box, and I'm taking an image from the other side. So this again has a Siemens stencil and also the M cutout and holes of different sizes. And the last experiment is of that same pistol attached to the body of a mannequin. Mannequin is painted in graphite paint to make it reflective, to make the reflectivity of the mannequin similar to human skin at 80 gigahertz. And then it's covered with this University of Michigan hoodie, basically. And we want to see if we can detect this gun inside the hoodie for concealed weapons detection kind of scenario. Okay, so these are the 5 experiments we'll go through. So without further delay, let's look at the code. So, okay. You can go to this link in this location. I'll provide this in the description as well. Download the file there, extract it into a folder called imaging raw data, which should have the 5 data sets and also the background measurement for each data, because we'll use background subtraction. All right, so let's look at the code. So it's just clearing everything. And then we have some parameters here, which I'll quickly go through. Bandwidth, center frequency, speed of light, I guess, and then the antenna beam within degrees. If you look at the notes again, we'll see that at the end, we use this truncation, which depends on the beam width of your antenna. If you don't know what it is, you can set this to like 180, I guess, but it's better to have it be the actual beam width of your system. Okay. RR is just the range resolution. I don't really use it, so it's okay if you don't know what that is. But range resolution is CO2 times the bandwidth, which also we derive in this somewhere down here, I believe. Yeah, there we go. Okay. Then this is the sampling rate of my A to D, the time period of my chirp, 48 microseconds. It's actually 50 microseconds is the chirp repetition interval, but 2 microseconds is dead time. So I have the chirp actually, the actual time of the chirp is only 48 microseconds. Number of fast time samples is the sampling rate times the chirp duration. And then since I said I'm using a down chirp, the chirp rate is minus bandwidth over the chirp duration. This is important. So if you're using your own data set with an up chirp, then make sure this is removed. dt is the time interval between each sample, total time of the pulse, and we set a convention, I guess, when we did the derivation for the time signal, the time array, basically to go from minus TP over 2 to TP over 2. So I'm using that here. This is the total range from the aliasing free range. And then we go to the slow time parameters, which is the raster scan that we did. So I'm going from minus 200 millimeters to 200 millimeters, both in X and Y, and I have a spacing of about 1.6 millimeters. So you need to make sure spacing is less than lambda over 2 or equal to lambda over 2. Since at 80 gigahertz, around 4 millimeters is the wavelength. I've set the spacing to be 1.6 millimeters. This is total number of slow time measurements, mx times my. So let's run the code till here, see what we get. So we've taken about 63,000 measurements. So that's a lot, right? And each one has 2,400 samples. So it's a huge data set, 3D data set. And that's why range migration you can only use really range migration for creating this image. If you try to use back projection, it'll take days or maybe even weeks or months. Maybe actually even years. So just do range migration. Okay. So here I'm using the first data set, which is the Siemens stencil and the background. So I collect the data of the background and the actual measurement, and then I have to rearrange the data set of the measurement because it's all just continuous 1D array that comes in. Let's take a look at that. So you see it's a huge 1D array because it's just samples from the sampler itself. Yeah, so we need to reshape that into the size that we want. So let me actually run this and you'll see what I'm saying. Okay, so now that we reshaped it, it is 2400 by 63,000 measurements, which is what we saw earlier, right? Which was M was 63,000, the slow time, and then 2400 is the fast time samples. Okay, and this calibration step 2, oh, sorry. So let me run this again, the first section. Okay, so what is this calibration step 2? I'll quickly explain it. If you can read the paper if you want, but essentially what's wrong is that in the system itself, since I have, these large waveguides and a huge antenna and everything, the phase center actually moves. So the actual phase center is somewhere here where you split into the TX and RX parts at the power divider. Go back here, somewhere around here, right? Because when you down mix or down chirp, everything up to here is removed. All the phase up to here, all of this, the phase of all of this is removed, but you have some extra phase delay in this propagation, and this propagation. But when we reconstruct the image, we assume the phase center is somewhere between the TX and RX antennas. Or if you're using a common antenna, then it's the phase center of that antenna itself. And this difference between these two can corrupt the image, basically. So we need to remove this extra propagation that goes, from here all the way here, and from here till this phase center, and then from this phase center back to this. So all these extra time delays I've calibrated out, and that's what that is. If you're using a chip or if you're using very short waveguides, this doesn't matter. But in my case, it does matter. So I've found that it's about 19 centimeters of extra time delay that I need to remove. And the way I did that is mentioned in the paper. So if you want more details, you can go read that. And why do I call this step 2? There is actually already a step 1 of calibration that I'm doing to remove the residual video phase and any chirp nonlinearities. That I do actually when I collect the data itself at each data point. And that is also mentioned in the paper. So if you want, you can read section 2 of this paper, where I go, section 3, sorry, the phase calibration. So step 1, nonlinearity calibration, and then step 2. If you're close to the antenna, if the target is close to the antenna or close to the radar system, the calibration step 1 can be skipped. But step 2 is important. Okay. So in this case, actually, I noticed that step 1 doesn't make much difference. Step 2 actually makes a huge difference in the reconstruction. All right, with that aside, let's move on. Okay, so the next thing I'm doing is I'm rearranging the data set from the raster scan into an XY grid. So right now, the data is stored in a raster scan format, right? Goes from here and then flips over and then flips over. So I'm flipping it back so that the data just starts from here, from left to right in each row, so that it's an actual XY grid. Okay, and then we pre-compute the K space. So I say, okay, KT is this gamma T over C plus omega C over C. This is again from the theory. And then I set the limit based on the beam width that I have. And then I truncate my K space. I create the K space, Cartesian K space in X and Y. And then I truncate it based on this limit here. And then I make a 3D, basically 3D matrix for KX, KY, and KZ. And KZ comes from the dispersion relation that we derived in the theory. So I suggest you go back and look at the theory if you don't understand these equations. But if you do, if you have looked at the theory, then they should be pretty straightforward. Okay, and then the uniform, KZ uniform, which we need to resample onto, I choose that to be the center of my KZ matrix. Yeah, and this I'm just using. I'm also making a 3D version of this. That's just for illustration purposes here. You don't really need that. Okay, so once I've created my K space, which is also a pre-computing step, this is an extra step that I've added in this section just for visualization. You don't really need this. So let's plot this and see what I get. Oh, oops. So let me go back and run the code step by step. Step 1, step 2. So this reformatting takes a few seconds because it's a bunch of for loops. Okay. And then pre-computing, that should be fast. All right, so then let's visualize the K space. Okay, so this is what I have, right? So this blue is the actual K space that we've sampled, right? If you look at, you go back and look at the video theory, you'll see that I discussed this here, right? So this is the actual K space. So now I've truncated this K space with my beam width, and that's why it doesn't go all the way down to 0. So you see, this is kind of the truncation part, right? We remove stuff that's beyond this. And now we need to resample onto a uniform grid K space like this, right? And that resampling will be done with the stored interpolation. So here I've not plotted the whole thing. If I actually plot the whole thing, you'll see what I mean. Okay, so this is what it looks like. So let's zoom into this region and see what it looks like. Okay, so now you see that, oh, sorry, I clicked that too fast. Zoom in, zoom in, zoom in. A little bit more, a little bit more, a little bit more, a little bit more. Okay, so you see that at the center, they're both about the same, right? Where we want to sample and where we have sampled and what we need to resample to. But if you go towards the edges, yeah, so you see that now that's the sampling rate of both of them is quite different, right? And if you play around with this a little bit, you'll get a better intuition probably, but essentially we need to resample onto this orange grid for each of these lines. And that's what the stalled interpolation does. Okay. All right. And of course we can't so let me go back, plot this again. So you see that this blue part is only covering this region, right? So we can't really interpolate here because the actual sample data doesn't exist. So MATLAB will try to extrapolate onto this, and then we'll remove all that extrapolated data and make all of it zero, basically. Because you can only really do an interpolation. You can't really extrapolate beyond where you actually sampled. But that's good enough actually to reconstruct. Okay, so that's what this is. Let me close this and move on. And then we finally move on to reconstruction. So now we have our actual data set, which is SB, right? The rearranged data set in 3D. So if you look at that data set, it's 251 by 251 by 2400. That's X dimension, Y dimension, and time dimension. Okay. So the first step is just a 2D FFT. Step 2 is the stalled interpolation. So for each X and Y in the KX-KY domain, I interpolate over Z, right? So I say, okay, what is the actual Z that it's on? What is the data on that actual Z? And then interpolate that onto the uniform KZ, right? So, and do that for each KX and KY. So that's my 2D stalled interpolation. And then I remove all the extrapolated data. I just set that to be 0. Otherwise, it would just be it would be a NaN value. Okay, so that's step 2, simple enough, interpolation. And then step 3 is just a 3D inverse FFT. So I take IFFT in X, IFFT in Y, and then a regular FFT in Z. The reason I'm not using an IFFT is because of the time convention. So the measured data is of a time convention, I think of e to the I omega t, whereas MATLAB uses e to the minus I omega t. So that's why that's why in the time domain, I just use an FFT. And that's something you need to play with and see what your measurement, the time convention that is part of your measurement. Okay. That's it. That's the third step. And then I record how much time it took. So let's actually run this part. It's actually fairly simple if you think about it. It's just a 3-step algorithm, right? So it shows you, okay, first step is done. Stalled interpolation is the next step. That's actually the longest step because FFTs are highly optimized in MATLAB. The interpolation would take the longest amount of time. You could actually combine step 2 and 3 into a non-uniform and do a non-uniform FFT in Z and then just a 2D FFT in X and Y. But I'm not doing that here. Okay, that's it. And then we plot the image. So here I'm just plotting it for different cuts of Z. And we'll proceed through all the cuts and see where we see the target. So as I click through, I'm clicking through different cuts. And then as we move on, you see it's starting to come into focus, starting to come into focus. And now it's in focus, right? And what's actually amazing is that the entire target is in focus. And then it starts fading out. And then interestingly, actually, you'll again start seeing it come in a little bit brighter at a slightly different Z distance and then become dim. Again bright, again dim, a little bit bright, dim, and then it finally dies out. So why does that happen? I could answer it or I could let you think about it, but it has something to do with the fact that actually I'll leave it for you to decide. So think about why that happens and leave it in the comments. And I can answer you in the comments below as to why. Let's do that again. So you see that It doesn't exist, and slowly starts coming into focus, but then becomes bright, and then again dark, again bright, again dark, and then fully comes into focus. Then again, it becomes dark, a little bit bright, a little bit dark, a little bit bright, dark, and then dies out, right? So the hint is that it looks kind of like a sync function. Bright, dark, bright, dark, bright, dark, becomes fully in focus, and then again bright, and then again dark, and then so on, right? So why does it look like a sync function? I'll let you think about that. That's already a big hint, actually, as to why sync along Z. Okay. Now I'll close this. So that's the first target that we looked at, which is the Siemens star. Can go and look at the other ones, I guess. So this should take a few seconds. Once it's done, I'll come back. Okay, so that took about 30 seconds. So maybe I should update this to say it should take 30 seconds or so. And let's walk through this and see what we see. So we see something is coming in. And there we go. So now it's fully in focus. And what's really amazing is that you can actually see these tapes, right? This tape and this tape. And if you look at, for example, the target, you know, these tapes are out here, right? And you can see exactly the same thing out here. Even more amazing is that if you plot the same figure in, for example, in dB scale, you'll also see the foam pad, right? Which is what I report in the paper. And the indent in the foam is out here. You can see there's a small indent in the foam here. Let me zoom in. So you see this indent here, that indent is there, the edge of the foam. And this extra stuff out here is all the side lobes from the strong metallic target. So that's pretty cool, I think, right? And then the same behavior again, it becomes dim and then starts to become bright again and then so on. Okay, that's about this target. So I'll do that for the next one as well. This is actually one of my favorites. So I'm gonna pause it for a second. Oops. Oh, sorry. There we go. Okay, so it's done. Computed in about 30 seconds. So let's again run through this and see what we get. So we start seeing the gun kind of coming into focus. And there we go. That's what it looks like. So if I step through once more, you'll actually see that there's still, this part is now coming a little bit more into focus. And that's because the gun was a little bit tilted back. So let me actually run through that again. So let's plot it again. Step through, step through. There we go. Okay, so I'll stop it here. Okay, I actually want to look at this more closely. All right. So you see, this is such a cool picture because you can see a lot of the features from the gun in the image. Right? So you see like this boundary of this little bit of rough surface here is kind of pretty clear, right? And then you see a small patch here with some striations, and that patch is showing up as some difference, something that's different here. And then this is an indentation with like some ellipses. That's an indent inside the metal. And you can see that that kind of shows up as well. Trigger, handle, very clear. And this line, which is like maybe like a millimeter across, showing up very clearly, right? And then you have an indent here, that indent shows up. And then these 4 or 8, I guess, indents that are very big, they also kind of show up here. And because actually this is a hole, here it acts like a cavity, and that's why SAR cannot reconstruct cavities very well, and that's why you don't really see the cavities very clearly. they get kind of smudged out because, I don't want to go into the details now, but SAR is not very good at reconstructing cavities. So that's why those cavities don't show up. But again, these lines here, since they're not exactly cavities, they do kind of show up. So this is really cool, right? Even at a distance of, let's say, like 0.3 to 0.5 meters, you can reconstruct such a good image of a gun. That's pretty cool, I think. Even this kind of like indent here, you can kind of see that there's an indent here, right? Really cool. Okay. So these targets, of course, you can see them very clearly, but let's move on to like a target like this, which is 3D, right? You have one region that is at a different Z than this gun. So what we want to see is, can it focus both targets simultaneously? And that's what it makes this system fundamentally different than, let's say, some other kind of imaging system. For example, using just a lens and focusing with the lens, that would only focus in one Z cut, whereas synthetic aperture radar can focus in all Z cuts over a long range. In fact, here, if you look at it, um, the total Z distance over which it's focused is huge. How much is it? So this is the total Z distance, right? And the maximum value is 45 meters. So let's assume, okay, 22.5 meters is the aliasing free range, right? We go back. Okay, I mean, the reason it's 22.5 meters is it's half of this because we are only using real data. It's not complex data. Because it's real data, the aliasing free range is only 22.5 meters. So the entire image is focused from Z equal to 0 to Z equal to 22.5 meters in just one shot, right? With this algorithm. That's what makes it so powerful. Okay, so let's look at the next data set. Run this. Okay, so let's look at what this looks like. So keep in mind, of course, that the radar is looking at this from the other side. So it's going to be flipped. But let's look at it. So as we step through, start to see something show up. And there we go. Okay, so now it's totally in focus, right? So you see the box, the cardboard box is showing up. And I mean, the fact that you can even see cardboard is really amazing in my opinion. That's the power of SAR. There's a huge amount of processing gain that you can get. You essentially have an aperture that's so big, and all of that gain adds up at each point. That's what's known as processing gain. So that's why you can even see something as weakly reflective as a cardboard box. Okay, and you can see the M symbol is showing up, and you can count the number of holes, 1, 2, 3, 4, 5. So even the smallest hole, which is about maybe around 2 millimeters across, is able to be resolved. Siemens star is very clear. And as we step through, eventually the gun comes into focus, right? So let me do that again. So that's one range bin, and that's the other range bin. And you can see in both range bins, this Siemens target is the stencil is kind of in focus because it's, I guess, between the two range bins. And then as we step through, you see the gun start to show up. There we go. So that range bin, the gun is quite clear. Again, you can see all the same features, which is wild, really. Despite the fact that it's sort of, now it's further away, it's 0.46. And if you remember from the derivation that the resolution doesn't change with distance for synthetic aperture radar. And that's why it's, again, you can see all features very well, even though the distance is close to half a meter, right? That's what makes it so cool. Okay, so I'm not going to step through all the way to 25 or 45 meters because that would take forever. So I'll just stop it here. And then this is the last one, which is the mannequin. So let's see what features of the mannequin or the gun we can see that's hidden inside the mannequin. So let me run this. So we want to compare with this one, right? Okay, it's done. Let's step through. I actually put this up for reference. You see something start to show up. And then there we go. In that cut, the gun is very clear, right? Again, all the features are visible, it's half a meter away. Still, you get all the features despite the fact that it's behind this hoodie. Interestingly, in the next cut, we see the handle a little bit better and we can actually see the shapes of the mannequin itself. So the chest, I guess, contours of the stomach, abs, all of that. So that's really cool. You can also see kind of the shadow of the gun show up, right? Sometimes, if the gun is not oriented correctly, if it's oriented at an angle, maybe you won't be able to see it very well because you have this specular reflection that goes away, doesn't come back to the radar, but you can always see the shadow of a target. And that's why it's important to be able to identify shadows uh, rather than weapons themselves. So this is a nice concealed weapons detection demonstration to show the power of synthetic aperture radar. Okay, so with that, I would like to conclude, I guess. The codes and everything should be available to you to download and play with it yourself. You can try different algorithms if you like, compare them, and so on. So that's about range migration. The theory is covered, experimental data and everything is done. Code is ready. You can play with it, try it on your own. In the next video, I'll talk about range migration for MIMO radar because I think we covered MIMO a little bit. So I think it'll be good to talk about that. I don't have experimental data for that, but I'll show you how you can, similar to the SAR demonstration for back projection, you can generate synthetic data and play with it that way. So that should probably cover the basic algorithms that I wanted to talk about in this series. I might take a break from the series after that and focus more on other series, the antennas and arrays part, the antennas and arrays series, or the millimeter wave integrated circuit series. There are a few other algorithms that I do want to cover here. There's the CSAR algorithm or circular SAR reconstruction, which I want to talk about. And maybe eventually I'll start continuing this series to talk more about spectral estimation techniques like music, Esprit, those kind of algorithms, which are a totally different set of reconstruction tools, but I'll see how things go. So hopefully this was useful. I think what we've covered so far is a good amount, good stopping point even. So we started with something very fundamental with FMCW, how FMCW works, and then built upon that using different demonstrations. And this is a nice conclusion to this part, to the videos that we made so far. So if you have any questions, leave them in the comments. You can send me an email. I've left my email in the description. Okay, with that, thank you so much. Have a nice day.